Greetings of the day, dear students. Today in this class, very one important topic, we are going to discuss about series resonance and parallel resonance, where most of the times you are going to get an essay in our end exam, and also you used to verify this series and parallel resonance in your laboratory also. You will be going to have one experiment on series and parallel resonance. First, we will discuss about the series resonance, where R, L, C will be in series, and there we will discuss about the resonant frequency and also about its half power frequencies omega 1, omega 2, and slowly we will discuss about the bandwidth, quality factor, and also some important points to be noted at resonance, and finally summary, and with one example we will conclude the series resonance topic. In that example itself we will find out the resonance frequency, quality factor, bandwidth, and current at resonance. Right now, let me enter into the topic. Before watching this video, you might have completed how to find out the impedances of a series RLC circuit. Impedance and admittance topic, you please watch. After completing that video, you please watch the series resonance. Right now, observe, dear students, if you are given a series RLC circuit like this, where the value of resistor having some resistance R and inductor L having, observe, j omega L is the inductive reactance expressed in ohm, and capacitor having some capacitive reactance 1 by j omega C. Right now, this circuit is said to be under resonance, very important, when imaginary part of impedance is 0. Imaginary part of impedance is 0. How do you understand? See here. First, find out the impedance. Impedance of series RLC. Z equal to R plus j omega L plus 1 by j omega C. Clear? Now, take out j common, omega L minus 1 by omega C. In this impedance, what is the imaginary part? Omega L minus 1 by omega C. You please make that imaginary part equal to 0. Then that is the condition where the resonance occurs. That is the condition where at that particular point of frequency, that frequency is called resonant frequency. Clear? Now, what is the imaginary part? Omega L minus 1 by omega C is made equal to 0. So, the value of omega at that point, you please indicate with omega naught resonant frequency. Now, omega naught L equal to 1 by omega naught C. Omega naught square equal to 1 by LC. Clear? So, what about omega naught? Omega naught equal to 1 divided by root LC. What are the units? Radians per second. Right? Now, but already we know that omega naught equal to 2 pi f naught. So, 2 pi f naught is equal to 1 by root LC. Therefore, omega f naught equal to 1 by 2 pi root LC. F naught equal to 1 by 2 pi root LC. Very important, dear students. What are the units? H. If it is simply 1 by root LC, the units are radian per second. If it is 1 by 2 pi root LC, the units are H. Clear? Yeah. Now, out of this entire discussion, the important point is you just find out the impedance and make the imaginary part of the impedance equal to 0. Make the imaginary part of the impedance equal to 0. Right? Yeah. Now, what will be the magnitude of current? Observe, dear students, at during resonance condition, right? Current I equal to V divided by Z, mod Z. And what is the magnitude of the applied voltage? Some Vm, right? And mod Z root over R square plus omega L minus 1 by omega C whole square, right? Now if you plot the graph, on x-axis taking the frequency and on y-axis taking the current, for different values of omega, you used to get a graph like this. And one more thing is, you should plot this graph on a logarithmic scale graph, semi-log graph, logarithmic scale on frequency axis. Clear? If you observe at resonant frequency omega naught, at some frequency omega naught, the current is maximum. Why? Because there the impedance is simply equal to root R square. Why? Because imaginary part is made 0 at the impedance at resonance. Because of this, what happened? Root over R square, the impedance is R. Simply R, Z equal to R. Very, very important. At what point? At resonance. Only exactly at resonance condition. At resonance. So Z is minimum. Current will be maximum. Clear? I repeat again. At resonance condition, the imaginary part of impedance is made 0. So that is the reason Z equal to root over R square, and that is simply equal to R. So the impedance is minimum, the current is maximum in series resonance condition, right? Yeah. Now let me observe the average power. So this is what here, now at that point of time, the value of current is simply current I equal to Vm by R. Very, very important. At a resonance condition, current I equal to Vm by R. Now observe, we will have two more frequencies, half power frequencies, omega 1 and omega 2. In this context, omega naught is the resonant frequency and omega 1 and omega 2 are the half power frequencies. How do you understand that word? At that particular point of current, right, the power will be exactly half of the power at resonance. The power will be equal to half of the power at resonance. That at that point of time, those frequencies are to be treated as half power frequencies. Clear? So first let me find out the average power. See here, what is the average power? I square R. But at a resonance condition, what is the current? Simply Vm by R. So the power will be half Vm square by R. Very simple. Now at certain frequencies, omega equal to omega and omega 2, the power dissipated is half the maximum power. Half the maximum power. Right? Now at that time, what will be the current? We will see now. Now power at omega 1 or power at omega 2 is equal to Vm square by 2R. Vm square by 2R is the power at resonance. And half of that value you have to consider. Now the same thing can be written as Vm by root 2 whole divided by 2R. Very, very important. Vm by root 2 whole divided by 2R. That means at half power, this is going to occur at some current magnitude which is equal to Im by root 2 indirectly. At a current magnitude, maximum current divided by root 2, 0.707 times the maximum value of current. There you draw a simple parallel line. There you draw a line parallel to the omega axis. Now extend it onto the x-axis, and the points where it intersects the x-axis indicate it with omega 1 and omega 2. Clear? Right. Now dear students, in this entire discussion, the important point is half power frequencies or lower cutoff half power frequencies are those at which the power dissipated is half the maximum power. Half the maximum power. Maximum power occurs at resonance. Why? Because at resonance Z is minimum, current is maximum. Okay, good. Next. Now you can find out omega 1 and omega 2 values. This derivation also you are having. Just now I have told you at half power frequencies we can obtain that. Okay, at half of the power, one rule is you simply make mod Z equal to root 2R. When the impedance is equal to root 2R, that is the point where the power is exactly half. So from that point what we can do, but actually what is mod Z? Z already we know. Under normal condition Z equal to R plus J of omega L minus 1 by omega C. It's mod Z root over R square plus omega L minus 1 by omega C whole square. You make it equal to root 2R. Now this root 2R can also be written as root over R square plus R square. Nothing wrong. The meaning is same. Root 2R is written as R square plus R square. Right? So indirectly, what does it mean? The value of this R is equal to plus R minus omega L minus 1 by omega C. R value is equal to plus R minus omega L minus 1 by omega C whole square. One time make it equal to minus R. Other time make it equal to plus. Now at one point let that omega at that value of frequency be omega 1. Right? Half power frequency omega 1. And during some positive sign take plus at positive you please take omega 2. Now just simplify this equation. You just bring it in the form of some a x square plus bx plus c equal to 0. At that time if you want the value of x will be equal to minus b plus or minus square root of b square minus 4ac whole divided by 2a. The values of the solution for this equation will be minus b plus or minus square root of b square minus 4ac by 2a. That is what we are going to do. We are going to find out omega 1 value and omega 2 value in terms of R, L and C. To find out the half power frequencies in terms of R, L and C, we are doing this derivation. The condition required is just like for resonance frequency, what you have done? We have simply made imaginary part of impedance is made equal to 0. So by doing so we got the resonant frequency. Now to get the half power frequencies you just simply make mod Z equal to root 2R. At this condition we will get the half power frequencies omega 1 and omega 2. Very clear. These two conditions are important. You should memorize these two conditions. Omega naught already we have expressed in terms of RLC. Of course R is not coming into the picture. How much value we got? 1 by 2 pi root LC. Similarly we should also find omega 1 and omega 2 known as half power frequencies in terms of R, L and C. Clear? That is what we are doing in this derivation. Now once you got the equation in the form some ax square plus bx plus c equal to 0 and minus b plus or minus square root of b square minus 4ac by 2a, on substituting the values we will get r1 omega 1 as minus r by 2l plus or minus root over r by 2l whole square plus 1 by lc. Very important. Similarly omega 2 value we will get it as r by 2l plus or minus root over r by 2l whole square plus 1 by lc. Now if you observe, if you just simply multiply omega 1 or omega naught, the relation between omega naught and omega 1 and omega 2, it is given by omega naught equal to root over omega 1 into omega 2. What does it mean? Very important. This statement number of times in competitive exams also he will ask. Resonance frequency is geometric mean of half power frequencies. Geometric mean of half power frequency. What do you mean by that? Omega naught is equal to root over omega 1 into omega 2. If you want to cross check, already you know the value of omega naught. What is the value of omega naught? Omega naught equal to 1 by root LC. You just simply multiply omega 1 and omega 2 and take the root for that. Right? We will get 1 divided by root LC. Clear? Yeah. Now in the diagram representation, in the graph, observe dear students. So this is the omega 1 value, now omega 2. Now this gap is to be called as bandwidth. Omega 1, this omega 2 minus omega 1, up to omega 2 minus omega 1, that difference we can but this bandwidth is also to be expressed in terms of RLC values. Now we will see that. Out of this entire discussion, the key point is you just bring the equation in terms of omega 1 and omega 2. Ax square plus bx plus c equal to 0, and just find out the roots. On substitutions you will get simply the answers, right? Yeah. Now what is the bandwidth? It is defined as difference between two half power frequencies. Very, very important. Two half power frequencies. What are the two half power frequencies we got? Omega 2 and omega 1. You just simply substitute the value of omega 2 and omega 1 and we will get R by L. The bandwidth is R by L. Okay. Now how do you define bandwidth? It's the difference between the two half power frequencies. Now we are having one more term, quality factor. How it is defined as the sharpness of the resonance in the resonant circuit is quantitatively measured by quality factor. How do you understand this word, the sharpness? Observe, dear students. For example, if you for resonance, if you got under for two different elements, you got a graphs like this. This is graph for one circuit, for one set of RLC values, and this one you got as a graph for another circuit, and this is a graph, one more graph for another circuit. Out of these three graphs, which one is having more sharpness? A or B or C? C is having the more sharpness. Its resonant frequency here it occurred, omega naught. And if you want to find out its half power frequencies, you please find out its maximum value and by root 2. Maximum value by root 2. Somewhere we will get here. For curve C, for example, Vm by root 2. Somewhere if you got here. Now with respect to curve C, this is omega 1 and omega 2. Observe, this is with respect to what? Curve C. This is the bandwidth. Bandwidth is high or low? Low. But observe for graph A, if it is very, very flat, if it is very, very flat, like this, for curve A, this is the maximum value. Maximum value, resonant frequency is same here only. But maximum value by root 2, somewhere you got here, maximum value divided by root 2. Now that root 2 value is cutting the graph here, and the other point is here. Now with respect to graph A, this is the bandwidth. This is the bandwidth. Very, very important. So if it is having more sharpness, the bandwidth region is less. Observe. If it is very wide or flat, the bandwidth is very, very high. The bandwidth is very, very high. Clear? Yeah. Now the sharpness of resonance in the resonant circuit is measured by the quality factor. How much sharpness it is. It is simply expressed in terms of observe here, dear students. observe here, it is simply the sharpness 2 pi peak energy stored in the circuit divided by energy dissipated in the circuit in one period at resonance. As we are having energy storing elements, 2 pi into what is the energy stored? Half Li square divided by energy dissipated across resistor I square R in one period, that is 1 by F at resonance, right? So half I square R into 1 by F, this is the energy dissipated, and this is the energy stored, half Li square. This is the average power dissipated in the circuit in one period, right? So on substituting these two, what we will get? 2 pi FL by R. But what is 2 pi FL? 2 pi F is nothing but at resonance omega naught into L by R, omega naught L by R. So if you observe, this quality factor is a dimensionless quantity because R is expressed in ohm and also omega naught L is also expressed in ohm, right? Or in another manner, we can write it as 1 by omega naught C into R. Very, very important. This quality factor, therefore Q equals to omega naught L by R. It is also same as 1 divided by omega naught C into R. 1 divided by omega naught C into R. Clear? Right. Now, what is the next summary? Now let me go into the summary. These are the, out of the entire discussion, these are the important points to be noted at resonance. The circuit given is R, L, C, and you have applied some voltage R, L, C, and some current I of t is flowing, right? And we have applied some voltage V of t. The first condition is imaginary part of impedance is to be made equal to 0 at resonance. Z equal to R, which is minimum. That implies current will be maximum. Very, very important. And at resonance, it is only purely resistive circuit. Voltage and current will be in phase. Voltage and current will be in phase. Keep in mind, dear student, all these are at resonance only. We are not saying during entire period of time I and voltage and current will be in phase. No, this is the condition only at resonance, right? So this is important. Z equal to R, and the voltage and current will be in phase. The moment we say both are in phase, from the previous basic, what will be the power factor? Cos 0 equal to 1, unity. So very, very important. The power factor at resonance is equal to unity. The power factor at resonance is equal to unity. Why? Because voltage and current both are in phase. Cos 0, 1. So this is one more important point. Now the impedance at resonance is equal to R, which is minimum, current is maximum, and the voltage, inductor voltage and capacitor voltage at resonance is given by VL equal to current. What is the current flowing through the circuit? Vm by R into what is the reactance of the inductor? Omega naught L. Current into reactance, just simply V equal to IZ. No, this is the impedance of the inductor, omega naught L. But if you observe, omega naught L by R indicates what? Quality factor. So the voltage across inductor will be Q times the Vm value. Vm, what does Vm here means? V of t equals to Vm at an angle theta V. Very, very important, dear students. The voltage across inductor will be how much? Quality factor times Vm. Very important. Similarly, the voltage across capacitor will be how much? At resonance. Current flowing through the capacitor Vm by R into impedance of the capacitor 1 by omega naught C. So this is also equal to quality factor times Vm. Quality factor times Vm. So these 4 points are very, very important with respect to the summary of a series resonance. Clear? Next, we will discuss one example with respect to the resonance. And of course, this is the summary. Once again, I will repeat you. Resonant frequency omega naught equal to 1 by root LC. If for this one, the units are radians per second. If you want to express it in H, f naught equal to 1 by 2 pi root LC. Bandwidth is equal to difference of the half power frequencies omega 2 minus omega 1. It is equal to R by L. And it is also same as omega naught by Q. Omega naught is the resonant frequency. Clear? Now the difference relation between quality factor, resonant frequency and bandwidth, very, very important. This one. Quality factor Q equal to omega naught by B. Quality factor Q equal to omega naught by B, bandwidth. Okay. So this is all about the series resonance. Okay. Next we will discuss the example. Now let me continue with one example, dear students. And in exams also, number of times problems are being asked on series resonance and parallel resonance, and moreover you will do this in your laboratory also. Yeah, let me complete this problem. Calculate resonant frequency, quality factor, bandwidth and current at resonant frequency. For in the given circuit, observe R equal to 1 kilo ohm, L equal to 100 millihenry, C equal to 0.1 microfarad. The first point should come to your mind. Resonant frequency omega naught equal to 1 divided by root LC. The common mistake most of the times students are committing is they are not writing this milli or micro. Directly they will write root 100 into 0.1. This meaning is 100. Immediately you should write 100 into 10 power minus 3. This is where most of the times mistakes are being committed. 0.1 micro, they are not looking at micro. Simply they are writing 0.1. You have to take it as 0.1 into 10 power minus 6. And one more thing is, while doing with calculator also, in the substitutions part, they are not taking this negative signs or numerator denominators properly, and they are getting the wrong answer. They are doing the substitution correctly. For most of the students we have observed this point. Don't think me otherwise. Why sir is telling like this? Right? For your sake only, my intention is you should not commit the same mistakes. I am telling all these points on observing most of the students. I don't want you to repeat the same mistakes. You may think, don't we know how to do this in calculator? No, but still some students in hurry. If you want to cross check, you just take a calculator and do this calculation and check whether you are getting this 10,000 radians per second or not. You have to write this 10 power minus 3 properly, and you have to maintain brackets properly, and you have to apply square root properly. And for the obtained answer, 1 divided by you have to take. If you are not able to do in the calculator in one attempt, in the first attempt, in a single step calculation, you do it step by step manner, and then finally write the answer. After doing substitutions also with the help of calculator, some of the students are getting the mistakes. Please don't repeat that. Right? Yeah. Now here, f naught equal to 1 by 2 pi root LC. This is nothing but omega naught by 2 pi. Already we know that. So we will get 1590.8 H. Better express it in kilo H. So it is simply 1.59 kilo H. Clear? Dear students, I repeat again. Please take care while expressing the units. 100 millihenry. Write it as 100 into 10 power minus 3. 0.1 microfarad. Write it as 0.1 into 10 power minus 6. While doing this with calculator, please be a little bit alert. Maintain the brackets, negative sign and square root, all these things properly while doing with the calculator. right? Yeah. Now what is the quality factor? All these formulas you have to memorize with respect to the resonance. Omega naught L by R. Omega naught value you know. Omega naught L by R. Omega naught you know. L value 100 into 10 power minus 3. This is important. R 1 kilo ohm, 1000 ohms. So you will get quality factor as 1. What about bandwidth? Bandwidth, the relation between bandwidth, resonant frequency and quality factor. Already you know the quality factor, you know the omega naught, resonant frequency. Now bandwidth B equal to omega naught by Q. Omega naught by Q. So 1000 divided by 10,000 divided by 1, you will get 10,000 radians per second. Otherwise, other formula for bandwidth is R by L. This is also okay. R is 1 kilo ohm divided by L, 100 millihenry. Same answer we will get 10,000 radian per second. Now what about at resonance? What about current? Current I equal to Vm by R. Vm divided by R. From the given problem, what is the applied voltage? V of t equal to how much he gave you in the problem? 20 cos of, what is the given? 20 cos 4t. V of t equal to 20 cos 4t. This is in the form of V of t equal to Vm cos of omega t. So Vm value is how much? Vm is 20. That is what you have done here. Vm divided by R. So you will get 20 milliamps. Now this is the current at resonant frequency. For example, if this is the graph, if this is the omega frequency axis, and if this is the current axis, and you will get this maximum value 20 milliamps at some particular frequency. This frequency is nothing but our resonant frequency. Now what about the current at omega 1 and omega 2? It is simply Im by root 2, this value. Now current at half power frequencies, the current will be this maximum value by root 2. At 20 by root 2 you will get the half power frequencies. This is omega 1, and this point is, if you extend it, omega 2. Now the difference between these two, omega 1 and omega 2, is our bandwidth. This sharpness is indicated by the quality factor. Clear? Now at omega equal to omega 1 plus omega 2, the voltage will be Vm by root 2. That is what we have done here. So at that point the current will be 14.14 milliamps. 14.14 milliamps. Okay. So this is all about the series resonance, and with one example. Okay. Please practice more number of problems, dear students, because easily you can attempt an essay from the series resonance, and moreover you will also have the same concept in the laboratory to do an experiment on this topic, right? Thank you.